was the couple that we understood in the previous class, right? Right? Do you remember this thing, Mees?
Yes, sir.
Yeah, and we also, so if we recall, if we recall this, that let's say you have this electric field and you put a positive charge in there, right? So this positive charge will experience some force in this direction, right? If you put a negative charge, so this will experience a force in this direction, right? Do you remember this force on a charged particle in external field, right? Can you recall this thing?
Yeah, sir.
Okay, so now we have similarly we have a dipole, right? We have a dipole. This is the dipole moment direction from negative to positive. And this positive charge will experience a force. This is the electric field in this direction. So this will experience a force in this direction. This will experience a force in this direction. This is negative charge. So we will have this kind of figure. One force in this direction, the other force in this direction. Right. And we know that what is the length of dipole? Length of dipole is 2a. So if I write this thing in here, so I have this thing, right? This is 2a. This force is acting in this direction. This force is acting in this direction. So you can see that both are equal amount of force. So they will create some rotational effect, right? And we will have this is the line of action, right? So we have to find out what is the perpendicular distance between them. So this is the perpendicular distance, right? This is the perpendicular distance. So how much would be this thing? You have this triangle. This is theta, you know, hypotenuse. This is hypotenuse. This is perpendicular. So what relates the perpendicular with the hypotenuse? What trigonometric ratio relates that? Mean? What trigonometric ratio relates perpendicular to hypotenuse? Yes, Neera, yeah. Can you recall what trigonometric ratio relates perpendicular to hypotenuse? Can you recall that? So sine theta is V by H, right? This
Yes,
relates
sir.
this relates perpendicular and hypotenuse. So I want to calculate perpendicular hypotenuse sine. So perpendicular would be 2a sine theta. Right? This distance is 2a sine theta. So now I have this perpendicular distance, I have this force. So what would be torque? Torque would be F and 2a sine theta, right? Because we know that couple is how much? Couple is force into perpendicular distance. This is the couple, right? So force is F, perpendicular distance is 2a sine. And we already know the amount of force, right? That is QE. So this is QE to a sine theta. And we know that what is the dipole moment, magnitude of dipole moment, how much is that? Magnitude of dipole moment, how much is that? So you are not revised, right? start revising. This is magnitude of dipole moment. This is equal to charge into separation, right? So charge is Q, separation is 2A. So 2AQ is dipole moment. Not to be confused with this perpendicular. This is perpendicular, right? Let me write it as perpendicular. This is perpendicular. So this 2AQ and this is E sine theta. 2AQ is P E sine theta. And can you tell me what is what is AB sine theta? What is that thing? What is AB sine theta? We have extensively done that thing. So what is AB sine theta? Can you record? What is AB sine theta? Yes. So just look at the previous thing, right? AB sine theta is A cross B. A cross B is AB sine theta, right? That is the definition of cross product. So which means that we are getting this PE, right? PE sine theta, A is P, P is E. So AB sine theta is cross product. So we will get the torque as a cross product of P and E. So this is the torque on our type, right? In an external electric field. So that is the torque. Is this thing clear to you?
Yeah, sir.
Yeah. So first one. Yes, hello, Assalam. Assalamu alaikum.
Assalamualaikum.
Walaikum assalam. So we just started and we talked about this couple, right? So we were talking about that the positive charge experience a force in the direction of electric field, negative charge experience the force against the direction of electric field, right? So this is QE, this is minus QE. So these two forces are equal in magnitude but acting in opposite direction. So then they will create a rotational effect that would be the couple, and we know that couple is force into perpendicular distance. So we calculate this thing and we got that torque is P cross P, right? So this is what we have studied so far. Okay, and we will talk about three conditions, right? So special case. So we know that torque is P E sine theta. Right? This is the torque on a time. And let's say we have this electric field and we have put the dipole like this. So this is minus Q and this is plus Q. So this is the way that I have put the dipole. So what is the angle between P and E? What is theta in this case? Yeah, what is theta in this case?
90 degree.
90, right? Because we already know that this is minus Q, this is plus Q. So dipole moment has this direction, right? So we know that dipole moment is this direction, right? Electric field is in this direction. So these are perpendicular. So sine theta is 90. This is first case. So theta is 90. So torque would be what? PE sine of 90. So this is 1. So for this case, torque would be maximum. This is the first case. Second case is that when you put the dipole second case. So you have this electric field, right? And you put the dipole like this. So what is the angle between T and E? What is the angle? Yes. What is the angle
Sir, 0
between
degree. Sir,
because yes, yes, you want to change your answer as well.
no, sir.
Okay, so this is P, right? This is E. So they are in the same direction. So theta is 0 degree, right? Theta is 0 degree. So this is called, and torque would be what? Torque would be PE sine theta. So PE sine 0 is 0. So this is 0. So there would be no torque, right? There would be no rotational effect, and there would be there would not any rotational effect because we are getting a torque which is 0, right? And this is called stable equilibrium, right? Why stable equilibrium? Because there will be no rotational effect, right? So that is why this is called stable equilibrium. Now we have the third case, which is the final case. So this is the electric field, and I put the dipole in this way, right? So what is the angle between electric field and dipole? Yeah, what is the angle?
Sir, 0.
0. So what is the direction of dipole? This is the direction of dipole, right?
Sir, positive.
Dipole. Yeah, this is dipole. This is electric field. So what is the angle? 0.
No, sir, 180 degree.
180 degree. So for this case, theta is 180. So torque would be how much? So torque would be PE sine theta. And we know that this is sine 180. So again, sine 180 is 0. So this would be 0. So again, there would not be any rotational effect. So again, there would not be rotational effect. But this is called unstable. These are the three special cases that I wanted to talk about. So torque on a dipole we have done. Remember, this is a very important quantity. Torque is P cross. So that is related with dipole moment and electric. So you guys please note down from here, right? Please note down from the couple part because you guys need it.
Excuse me, sir. I have
Yes.
a bit of a problem. Thing is that I don't exactly have my this note writing pad and all, so I
Yeah.
can't really note it down.
So you have to just take this screenshot, right?
No, no, sir. My phone currently is in charge, so I'll have to wait like a few minutes before it can actually.
Oh, so you are joining with the laptop, right?
Yes, sir.
So in laptop you can take the screenshot, right? Print screen is there is command print screen.
Yes, I'll see if I can do that, sir.
Yeah, yeah.
I think so. My phone will have enough charge. I mean, I just need to take pictures, right? So I think so. I'll have enough. I'll just check, sir. Just check.
Yeah, just press. So you have this print screen button, right? In your laptop, when you look at Control Shift Enter in the right hand side, whenever you use this numerical numbers. So above the backspace, you have this delete button and you have this print screen button. So you can use that print screen button to have this screenshot. Uh, okay, Mir, you note it down. So whenever you guys have noted it down, you want to scroll down. Yes, whenever you guys want me to scroll down, please. Yeah, whenever you guys want me to scroll down, please let me. Yes, I noted everyone. Me and Ursula noted for taking this screenshot. Please tell me we have to hurry and finish this chapter.
Yes, sir.
Done. So, yeah. Yeah, whenever you guys want to scroll down, please. Okay. Yes, Archana and me. Tell me.
So can you scroll a bit up? Missed some part. Scroll a
Oh,
bit up, sir.
up. Okay, which part? This part is
So
it?
all the way up.
All the way, all the way up. Yes.
Yes, sir.
Which one? This one is from.
Okay, fine. Yes, yes, not
This
this one.
one
A bit down.
is.
Sir, a bit down, a bit down. Sir, sir, down. Yes, sir.
Yes.
Yes, sir. Scroll
Yeah.
down.
Do you have any comment? No. This is okay. Yes, because otherwise we would be repeating this chapter again and again. And if you guys don't revise this, then
Yes, sir. Scroll down, sir. I meant this part.
yeah. So then please,
The wait, let me take.
yes,
Yes, sir. Just wait. I need to take the screenshot, sir. You're
yeah,
scrolling a
yeah,
bit
yeah.
too fast.
No, no, no. So you tell me that where should I put the screen? Then I will put the screen there.
Just scroll a bit up.
Okay.
Yes, sir. A bit more.
Okay. Yes.
Sir, above this, sir. Above this part. I think so. I took a screenshot, but it's not showing, sir.
This one.
Yes, sir. I took a screenshot of this up. It's not showing. It's showing now, sir. It's showing now.
Yeah, maybe. Oh, where should I put the screen?
Yes, sir. Just scroll down, sir. I'm done with this part.
And what about this part? Me, you can also tell like
Yes, sir. I'm done.
that. So then,
Yes, sir. This one done.
done. Okay, so then other.
Yes, sir. Done.
This one also done.
Oh, yes, sir.
Okay, me, yeah. What about you?
Yes, sir. Done.
Okay, so then please done. Last. So this is the thought in an external field experienced by the time. And now the last topic we will start. So whenever you guys have put it,
Yes, sir. Done with this.
Done. Okay, so now let us talk about the other topic, which is electric. My energy is a bit down. Before we talk about this electric flux, we should understand about the right. So, what kind of surfaces we can have? So, you are looking at your laptop, right? That is one surface. Surface means that it has two dimensions, right? And the important thing about the surface is the area, right? So, you have these surfaces. So, when you are looking at your screen, so that is one kind of surface. And when you are looking at, let's say, yeah, yeah, this notepad also, right? So this is one kind of surface, which is same as the screen one, right? So this one notepad, same surface, right? And this mobile one, same surface. So all these are surfaces. But you can also have, let's say, football, right? So football is also a surface, right, guys? This this box this box is also some surface, right? So what is the difference between the football and the screen that you are looking? So what is the difference that you can tell? What is the difference, guys? Yes. When you are looking at your screen or the mobile surface or the notepad that I have showed you, and when you look at the football and the box, so what difference can you make about these two surfaces? Any clue, any idea, anything that is coming into your mind? Yes. So there are two kinds of surface. One is open surface, and the other one is this closed surface. Right. So your football, your cylinder, your whatever box, these are closed surfaces, right? And then you have these open surfaces which are what circle, right? Or let me write disk because the circle is not a surface, so disk. And then you have this, let's say, board. So these are some open surfaces, right? So let's see you have these surfaces. So for the surfaces, we talk about area, right? And area is a scalar quantity or a vector quantity. What kind of quantity is this? Is what kind of quantity, guys? Yes. Vector is a vector quantity. The important if we have a surface like this rectangular surface, right? This is one of the surface. So, what would be the direction of the area vector? Area is this, right? Area is this. So, what would be the direction of this area vector? So, the normal to this plane, normal to this plane, that is the direction, right? So, normal to this plane is normal to this plane is the direction of area vectors. Clear? Is this thing clear? So if I have this kind of a shape, this circular thing, so what would be the area vector? Area vector would be normal to this, right? Is this thing clear? Yes, guys? Is this thing clear, everyone? Yes, guys, is this thing clear? So is this thing
Yes, sir.
yeah. Okay. Okay, so these are the area vector and their direction. So if I say, right, if I say XY plane, so let me write plane area. Right, so if I say this is X, Y, and Z. So this is my XY plane, right? This is my XY plane. So what would be the normal to this vector? What would be the normal to this vector? Yes. For XY plane, the normal would be in which direction? Yes, you guys think about it and this is YZ plane. And this one is X. This one is X. Z, okay. One plane is this one. One plane is this one. Other plane is this one. Dark plane. This one is the other plane, right? So just look at the corners of the wall, right? So you have these walls, and the other is this one. The other one is this one. Okay. So this is your floor, right? This is the floor. These are two walls, and these are the corners. So if I am talking about this XY plane, so normal to this plane will point out to which direction? Normal to XY plane would be which direction? perpendicular to xy plane, what would be the direction, guys? Please think and tell. Have x, y, and z, right? So this is x, this is y. Perpendicular to x, y is which direction? Which direction is perpendicular to x, y? Yes. Which direction is perpendicular to x, y? Which direction is perpendicular to x, y? This is your y, this is your x. Which direction is perfect? This z direction,
Z.
z, right? So this z direction is perfect. This is your x, this is your y, and perpendicular, this is the plane. This xy is the plane, and the perpendicular to this plane is this z direction, right? Similarly, if you take a yz plane, right? So I'm talking about these directions because these are very important in flux. So normal to xy plane is k hat, right? So if you have a xy plane, in xy plane, in xy plane, area vector direction is k hat. In yz plane, area vector direction is x or I hat, and in what in xz plane, right? In xz plane, area vector direction is g hat. So these are the directions. Okay. Now let us understand about the flux. So what is flux? So electric flux is the total number of electric field lines passing normally to the surface, right? So these are called the electric flux. So if we have this area, if we have this disk, and these are the number of electric field lines passing through this area, right? So this would be how many electric field lines are there? How many electric field lines are there?
Sir, 4.
Yes, 4. So electric flux would be 4, right? So this is the definition of electric flux. Total number of electric field lines. This word is very important. Passing normally to the surface. Passing normally to the surface. This is the surface, right? And let's say the electric field lines are passing this way, right? Electric field lines are passing this way. So these are not passing normally, right? This is our normal direction. This is our normal direction, right? And electric field lines are passing this way. So we will count the normal component of this electric field line, right? So electric field will have two components. One would be this thing. One would be this is theta, So this would be perpendicular, and this would be this normal, right? So this is e cos theta, right? This is e, so this would be e cos theta, and flux is defined as e dot a, which is e cos theta. Right, so this is the dot product. Okay, is this thing clear, everyone? Is this thing clear? Yes. Is this thing clear, everyone? Is this thing clear? Yes, guys, Arsalan and please, what are you guys? Is this thing clear? Are you guys there, Arsalan and me? Are you guys there? Hello, can you guys hear me?
Yes, sir. Yes, sir.
Yeah, so is this thing clear? Arsalan, what is happening? Did you go to wash again? Yes, Arsalan, where are you?
Yes, sir. Yes, it's clear.
Yeah, I was. Okay, please note it down, and then we will do a couple of questions. So you guys understood what is electric flux? Electric flux is the total number of electric field lines. Electric field lines we already know. So electric field lines passing normally to the surface. Right.
Yes, sir. Done.
Done. Okay. Yeah, then please note down once. I should write. These are the direction of the area, right? So direction of area.
Yes, sir. Done.
Yeah. Okay, then please down.
Yes, sir. Done.
Okay, so fast. Me, what about you? Done for you also.
Yes, sir.
Yeah. So what are? Yeah. Then please down this part. Yeah, noted. Oh, this thing is very big to right. So noted this thing. Yes, guys, noted.
Yes, sir, it's done.
Okay, so then let us do some questions. So the electric is right, and this is so electric field is what Newton right, and and the area vector is given by this is also sometimes written as S, right? So A is 2I plus 2J minus 2K meter square, right? So you have to find out that find the electric flux, right? So we know what do we know? We know that flux is E dot A. So E is given this is 2 pi plus Ej plus 4K dot area is how much? 2I plus 2J minus 2K. So what would be the dot product? And this is how much? So Newton meter cube, right? So what would be this thing, guys? Oh, so this is why did I write Newton meter? So electric field is Q F by Q, right? This is Newton per meter. So this would be Newton meter square per. So how much would be this? You guys already know the dot product. What would be the value? Please tell me. I have told you guys about the dot product. Scalar product you guys already. So what would be the dot product, guys? Yes. What would be the dot product? Yes, guys. What would be the dot product? E vector you know, A vector you know. So what would be the dot product, guys? Please calculate and tell me dot product would be how much. Because this is very trivial. If you guys don't know this dot product, then it would be this is very easy. Dot product, vector product, vector. You guys have to remember in your fingertips. So please do this calculation. You guys have to revise some portion. Otherwise, it would be difficult. Yes, guys. You guys recall the dot product. Which part survives in the dot product? Which part doesn't? You guys have forgotten everything. So this is Very, very bad, guys. You guys have to revise. Otherwise, it would be pointless if we do all these, right? If you don't remember the previous things, so you guys have to revise. Otherwise, you won't remember this thing. And yeah, in the last, you will find this pretty hard. You guys have to revise all these. So dot product only the I dot I survives. I dot I, J dot J, K dot K. These are the things which survives, and I dot J or J dot K. All these things are there. And opposite to the cross product. In cross product, there doesn't survive. So this would be 2 into 2 plus 3 into 2 plus 4 into minus 2. This would be 4 plus 6 minus 8. So 10 minus 8 or 2 Newton meter square. So this is right. So you can have a similar kind of question that so similar kind of question that in a in some plane, let's say XY plane, right? So in some plane, this is making an angle. Yeah. So from this plane, the electric fields are making an angle which is let's say so this is the thing. So this angle is 60 degrees, right? And electric field is magnitude of electric field is given. This is let's say 15 Newton per coulomb, and magnitude of area that is also given. So this is 3 and 3 meters square, and this theta is given. So is this thing a normal to the surface area? So what is the angle that we count? Is this the angle that we count for the case of right?
Sir,
Which
we
angle?
count the one that's closer to 6 degree.
Yeah, we count the angle between the normal, not this plane. We count the angle between
Oh,
the
yes.
normal and this electric field, right? So from this surface, it is 60 degrees. So from this normal, this would be 30 degrees, right? So theta is 30 degrees. So
Sir, how
your
do you determine that? Whether it be 30 degree or 6? Oh, sir, I get it, I get.
yeah, yeah. So this is 90,
Yes,
right?
sir, 90 degree and 60 degree first, then 30 degree. Okay,
Yeah,
sir.
yeah. Yes, absolutely. So, and we know that what is flux? Flux is EA cos theta, right? So, in some question, they will give they will give this IJK Cartesian form, or in some question they will give the magnitude and the angle. So, if we apply this thing, E is 15, A is 3, cos of 30. So, cos 30 is how much? 3 by 2, right? So this would be 45 right, and then Newton meter square. So this would be the answer. You guys please note these things down, and then we will understand about the yeah. So we will understand about the cost.
Sir, I have a bit of doubt in this dot product
Yes,
problem.
yes, yes, yes.
Yes, sir. In this box, it's written I into I is equal to J into J, which is equal to K into K.
Yeah.
And in the equation, as you can see, you multiply it 2I into 2I, 3J into 2J, and obviously 4K into minus. I
Yes.
can't.
Yeah. Yeah.
Yes, sir. So my doubt is that does this formula only apply if the values are only 1i or 1j or 1k, or because in this equation shouldn't if it did apply, shouldn't it be that 2i into 2i will just become 1?
So you
And
see that I dot I is 1. So 2i and dot 2i. So these are some numbers. We can take it outside, right? So we can write this as 4 I dot I, right? And we know
hmm.
that I dot I is 1. So this would be.
Okay, sir. Okay.
Yeah, we just, these are numbers, right? Vectors multiplied with some numbers. So we can take it outside. We take these things outside and we take I dot I.
Okay,
Because,
sir.
yeah,
Yes,
whenever
sir.
you
You
guys,
can scroll down, sir.
what I will do is that I'm not going into detail and I will all, because if we go into the detail, then it would be difficult to complete this chapter. What I will do is that,
Yes, sir. I'm done.
yeah. Meet, what about you? Done, Meet.
Yes, sir.
Good. Okay, so next, now we know flux, right? So we also know the open surface, and we also know this closed surface. So we have this Gauss law, right? And what does it tell? So I wanted to talk about this curved surface, right? So I wanted to talk about this curved surface. We only talk about these kind of surface, right? And we only talked about these kind of surface. These are not curved surface. This surface is a curved surface, right? This surface is a curved one. So if I draw the surface like this, right? So this surface is a curved one. And for this kind of surface, if I take the angle, so this angle would be different for every kind of electric field lines, right? Electric field lines are same, but this angle is changing, right? So if I take this thing, so this is small, this has increased, and this is again different. So for the curved surface, these angles are different. So what we do is that then what we do for curved surface, we write phi as integral of E dot ds, right? And we use this thing in such a way that these are parallel to each other, right? So these surface will have this direction, right? And these, if I take the electric field lines in such a way that these are parallel, so this would be simply E or ds, right? In some surface. So this is the surface integral, right? I will not go into the details, but this is important. Okay. So this is the surface integral. And what do we have? So we have this Gauss law. What does it say? So the total amount of flux in a closed surface is equal to equal to 1 by epsilon naught times the charge enclosed by the surface. Right, so this is the Gauss law. So let's say that if we have this sphere, right, and some charge q is placed inside this sphere, right, and electric field lines are passing like okay. So Gauss law states that the flux would be simply Q enclosed by epsilon for a closed surface. Right, this sphere is a closed surface. So is this thing clear? Is this thing clear?
Yes, sir.
Okay, so we use this Gauss law for two kinds of system. One is the discrete system, right? So we talk about the continuous system at some point later. So first, let us talk about the discrete. So let's say we want to, yeah. So let's say we want to calculate, find the flux surface given in the right. So we want to find the surface right through this thing, and the charge is placed at let's say a distance from this surface. So you want to calculate the we want to calculate the flux through this surface. So how much flux is passing through this surface? Okay, is this thing clear?
Yes, sir.
Okay, and what do we know? We know the Gauss law. What does it say? So it says that in a closed surface, the flux is simply 1 by E naught times the charge, right? So I have this plain sheet, right? And one idea that I can use is that I can make this surface a closed one, right? I do some things in such a way that this becomes a closed surface. And then I know that, then I know that it would be, then I can use this Gauss law and I can easily calculate the flux through this surface, right? So let's say that, so let's say that let's say I have this surface, right? This is the surface through which I want to calculate the flux. And my charge is kept at here, right?
Yes.
So I want to make it a closed surface. So what will I do is that I will make a surface in this way, 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 and I will put a surface in this way. So this will become a cuboid, right? So it will become like this. So I had this surface, right? I had this surface, and I make a surface here, I make a surface here, I make a surface here, I make a surface this one, and I may put a surface in here. So then this charge would be inside this. So then this charge would be inside this thing, right? Then this charge would be inside this closed system. So did you guys understand this part? Yes.
Yes, sir.
Okay. And yeah, so this is not a cuboid. We will make a cube, right? Because if we make a cuboid, then the answer would be okay. So what I will do is that I will make surface closed. So I will make a surface which is closed to this one, right? So this will close this thing. Let's draw it properly. This thing and this thing, this thing, this thing. So now this is a closed surface, right? This is a cube. So we know that for this cube, right? For this cube, the flux is how much? For how many surfaces are there? For cube, flux is q by epsilon 1, right? This is the charge which is inside this surface, right? So how many surfaces are closing this thing? How many surfaces? So six,
Sir, six.
yeah, six surfaces are closing this thing, right? So for one surface, because I want to calculate for this, so this is one surface, right? So one surface would be q by this six will go in this side. So this would be the flux passing through this, right? So let's say this is phi one. So phi one is this thing clear? Is this thing clear, guys?
Yes, sir.
Okay, so then I will, yeah, so then I will use the Gauss law. So Gauss law in the continuous form, it is written like so another form of Gauss law. So Gauss law for continuous. This is written as B dot ds, right? This is equal to Q enclosed by epsilon. So this is the Gauss law in integral form, right? Gauss law in integral form. I have skipped so many things because I want to cover this thing very quickly. Which are the important ones? I will talk about those things on. Gauss law in integral form, right? And using this thing, we used to calculate the electric field of infinite wire. We also calculate the electric field of infinite sheet, and we also calculate the electric field of hollow sphere. So these are the applications of Gauss. Okay, so yeah, so how do we apply the Gauss law for this case? Right. I will talk about these things, but before I do that, you guys please note down this. Right. So you guys please note down this. Please note down this.
Yes, sir. Scroll down. Yes, sir. Scroll down.
Done. Okay. There's one more question that yeah, that I will talk about. some other- Oh, so this is 6 epsilon.
Yes, scroll down. Yes, scroll down.
Yeah, this is that. Okay, so now we will try to calculate these things, but before we do that, we know that what is Gauss law. So to apply the Gauss law, right? There is more simplification is done so that integral becomes right. And how do we do that? To do that, we use Gaussian surface, right? So what does this Gaussian surface do? So we know that what is the integral, right? So use of Gaussian surface. So we take a hypothetical surface in which first case is that my E dot, so my electric field and area element vector becomes parallel or perpendicular, right? I choose the Gaussian surface in such a way that E and ds becomes parallel. So if this becomes parallel, so this would be EDS simply, right? Because we know that EDS is how much? E dot ds. This is E ds cos theta, right? So if this becomes parallel, so theta becomes for parallel, theta becomes 0. So E dot ds becomes simply E ds, right? And for perpendicular, theta is 90. So E dot ds becomes what? Cos 90 is how much? 0. So this becomes 0. So in this way, we can simplify this integral, right? So that is the purpose of this Gaussian surface. And also, I choose my Gaussian surface in this that my electric field becomes uniform, right? So that I can take out this electric field outside of the integral, right? Because this is uniform, this is constant, so I can take it outside and then I'll have to just integrate this surface area. Is this thing clear, guys? So these are the purposes of these Gaussian surfaces. So
Yes.
when we will do this, application of Gauss law, then you guys. So let us try to understand this with yeah. So with the electric field of infinite linear wires, linear charge. right? So what are these things? Linear charge, surface charge, and volumetric charge. So there are three kinds of right. So before I do that, let us talk about kinds of continuous. Right. So there are three kinds. One is linear charge, right? The other one is surface, and the other one is volume. Okay. So linear charge, as you guys can see that we have this line of wire and the charges are placed in this line, right? Maybe positive or negative charge. So this is the linear charge. And for this linear charge, we define a linear charge density. Linear charge density. So what is this linear charge density? So you guys know that what is density, right? Density is something by something. So if this is linear, then you will have L, right? This is length. If this is linear, then the denominator would be length. And we are calculating charge density, so this is Q. So this is called the linear charge. And if we want to calculate surface charge density, that is represented by sigma. And this is charge density, so this would be Q. And what would be in the denominator, guys? What would be that? Yeah, what would be that in the denominator? This is surface, so area would be there. Okay.
Hmm.
And then we have this volumetric charge. This is denoted by rho and Q by what? What would be there? P, volume, right? Volumetric charge. These are different kinds of charge density. So for linear wire, we'll talk about linear charge density. For hollow or finite sheet or sheet or yeah, for sheet we'll talk about this, and this part is not there for solid cylinders or spheres. So these are not in the syllabus. So we'll talk about this thing and the next class hopefully that. So you guys please note down these things, and please in the next class please revise, and then otherwise it would be very, yeah. So you guys
Yes, sir. I wanted
can,
to ask, can we read the previous recordings of the video so I can revise through that also?
yeah. So yes, you can do that. So
Okay,
yeah,
sir. Thank you.
yeah. I will send you those. So I will talk to the Learnivio team and then send you those. Where the videos. Okay, yes, please note it down, everyone.
Yes, sir. Scroll down. Yes, sir. Scroll down.
That is done.
Yes.
Yes, Mir, note it.
Okay, sir. Assalamu alaikum, sir.
Yeah. So Mir, did you note down this part?
Yes, sir.
Done. Okay, so we'll see you guys in the next Monday, but tomorrow, yeah, tomorrow is the last topic that. And yeah, on Monday we will talk about this. Yes. See you guys, and you guys have this class assessment, so please, whenever this class ends, please take that.
Okay, sir.
See you guys. Allah Hafiz. Allah Hafiz to
Allah Hafiz, sir.
everyone.